Welcome to technically grade 12 electrostatics. Okay, this is going to be in your matric final exam, so please make sure you focus and you understand what's going on with the whole rest of this electrostatic section. Okay, so we're doing Coulomb's law today. Coulomb's law states that 2-point charges will exert an electrostatic force on one another, and the force will be, here are your marks, the red, directly proportional to the product of the charges, and your second mark, inversely proportional to the square of the distance between them. You will note that this is very similar to Newton's law of universal gravitation. Hey? That one says that the force that two objects exert on each other is proportional to the product of the masses of the objects and inversely proportional to the square of the distance between them. So very similar to Newton's law of universal gravitation. So if you know one, you know the other one. In maths, okay, so actually, oopsie. Sorry. Okay, wait, let me pause you. Sorry guys, I don't know how that happened. Okay, so when we talk about this electrostatic force, okay, this electrostatic force that we're talking about, it is a force, and forces are vectors, okay? Very important to remember. Force equals a vector, and this is the same as the forces we've been dealing with the whole time. Force measured in newtons, except here it's a non-contact electrostatic force. Okay, now because a force is a vector, that means when you are asked to determine the electrostatic force, you need two things. You need the magnitude of the force, and you need the direction of the force. Okay, so we're going to split up how you calculate those. To calculate the magnitude of the electrostatic force, so the size, I know some of us panic when we see the word magnitude. Magnitude just means the size, the number associated with it. Okay, so to determine the magnitude of an electrostatic force, we use Coulomb's law. There's an equation that says the same thing as what the law says. Okay, and that equation is that the force experienced, okay, is proportional to, so I'm putting an equal sign here, I'll fix that. Okay, let's actually just do what it says. It's proportional to the product of the charges, okay, it's directly proportional to the product of the charges on each of our point charges. So let's say we're talking about charge 1 and charge 2, and it's inversely proportional, so now moving to the denominator, inversely proportional to the square of the distance between them. So again, we're using r to indicate the distance between them, so it's inversely proportional to r squared. Now, a proportionality relationship is all good and well, but it doesn't help us to do any calculations. So what we do is we change our proportionality relationship into an equation, and we include, or we introduce a proportionality constant, k. Okay, and that proportionality constant k, and this will be on your data sheet, is equal to 9 times 10 to the 9. Okay. And let's just label the rest of our variables while we're at it. If this is the electrostatic force, the magnitude of the electrostatic force, okay, measured in newtons. Q1 and Q2 are the charges of each of our point charges, measured in coulombs, and R is the distance between them, and that is measured in meters. Okay, so just be aware, keep your eye out for these two, for the charges and for the distance between them, especially. Those are often given to you in the question in the wrong units. Okay, make sure you do proper unit conversions where required. Okay, so that's how you would determine the magnitude of the electrostatic force. But because it's a vector, we don't stop at magnitude. We also need to determine the direction. Okay, so to determine the direction of an electrostatic force, do I need to move you down a little bit? Okay, so to determine the direction of the electrostatic force, we make use of logic, basically, and the fact that we know that opposite charges attract and like charges repel. Okay, so we're going to use the fact that we know that opposite charges attract and that like charges repel. Okay, so I'm just going to do a little example here. Let's say I had two charges. Let's say I had charge A and charge B, and charge A's charge was negative something, and charge B's charge was positive something. and we were interested in the electrostatic force experienced by A, we would use we would use Coulomb's law to determine the magnitude of that force, and to determine the direction, we would look at the signs here. Okay. Now to determine the direction based on the signs, you have to remember these two things. So I've got opposite charges. Opposite charges attract. That means A's electrostatic force will be towards B. It's an attractive force. Okay, on your notes, I think I've done all the different options. So if they're both negative, if they're both positive, if that's positive and that's negative. But the basics here is that you remember that opposite charges attract and like charges repel. Based on that, you can determine, well, where would A want to go? Would it want to go towards B or away from B? Is it attractive or is it repulsive? Okay. Also, just a little note. I don't know if I've included it here. I have included it in your notes. That when you substitute Q1 and Q2 in, okay, when you do this in your formula, please, please, please exclude the signs. Okay, so if we look back here, say A was negative 4 coulombs and B was positive 2 coulombs. When we substitute those values in for QA and QB, you wouldn't put your negative 4, you just put 4. And you wouldn't put your positive 2, you just put 2. Okay, so please make sure you exclude the signs of the charges. So for the magnitude, you don't use the charges, the signs of the charges. And for the direction, that's when you come and you look at the signs of the charges to determine is it towards or away from, attractive or repulsive. Okay, I'm going to pause you there and we're going to do a few examples. They're the same examples as the ones on your notes. Okay guys, so here's your first question. We've got charges A and charge B. So charge A has a charge of positive 1,28 times 10 to the negative 12. It's 15 centimeters away from charge B, which has a charge of positive 2,13 times 10 to the negative 13. And they want us to determine the force exerted on B by A. So in your notes, I have not drawn a little diagram of it, but I'm going to draw it here because I am visual and it helps me to understand the question. So there's my A and B. This cookie is dry. Okay, there's my A and B. A has a charge of plus 1,28 times 10 to the negative 12. B has a charge of plus 2,13 times 10 to the negative 13, and they are a distance of 15 centimeters apart, and we want to determine the force exerted on B by A. Okay, so we're going to use Coulomb's law here and to determine that force, and remember force is a vector, which means we need magnitude and direction. So I'm going to split it up, first looking at the magnitude. Okay, we're going to use Coulomb's law, which says that the force experienced is equal to our proportionality constant times, now on your formula sheet it says Q1, Q2, but I've got names for my charges. They're A and B, so I'm going to call that QA and QB over the distance between them squared. Okay, now we're going to substitute in our values. K is 9 times 10 to the 9. QA and QB are both in coulombs, beautiful, so I don't have to worry about doing unit conversions. So I can just substitute them in, excluding the signs. So it's 1,28 times 10 to the negative 12 and 2,13 times 10 to the negative 13 over the distance between them. This needs to be in meters, it's in centimeters. So I convert it to meters, that's 0,15 meters squared. Two things here. Don't forget to square it, please. And the second thing is, when we convert from centimeters to meters, you divide it by 100. There are 100 centimeters in a meter. Okay. And we just chuck this in on our calculator. And I don't know what my calculator is. Oh, I've got it here. Okay, we get 1,09 times 10 to the negative 13 newtons. Okay, so we've determined the magnitude, but we're not done. We also need direction. Okay, so for direction, the force on, what are we doing? Exerted on B. Okay, so we're interested in the force on B. So B is positive, A is also positive. which means the force we're going to experience is a repulsive force, right? And because it's a repulsive force, because they're both positive, that means that B is going to want to move away from A. Okay, so we can therefore come up with our full entire answer, which is that the net force, or the force, experienced by B as a result of A is equal to the magnitude of 1,09 times 10 to the negative 13 newtons, and the direction is away from A. Okay, it is a repulsive force. Okay, that's it. Okay, I'm going to pause you. We're going to do the second example. It's the same example as what is on your note. Okay guys, here's your example 2. We've got charge A and B with identical charges. When they're placed 2 meters apart, they exert a force of 2,13 times 10 to the negative 18 newtons on each other. Okay, so again, I'm just going to draw a little diagram of this. So we've got charge A and we've got charge B. We know that they are 2 meters apart, and we know that the force being experienced is 2,13 times 10 to the negative 18 newtons. Okay, question A. Will the force on A be towards or away from B? So this is a bit tricky because they haven't given us the charges. If they told us the charges on A and B, then we'd be able to look at that and see, is it repulsive or attractive? But they have told us that they have identical charges. That means that the sign of the charges is the same, which means it's a repulsive force, which means it will be away from B. Okay, so you can say away from B. If they then asked you to explain this, you would say that the charges are identical. Okay, and because they're identical, we have a repulsive force. Okay. Then question B says to determine the charge on each particle. We know the electrostatic force being experienced. We know the distance between them. We know that the charges are exactly the same. So we can use Coulomb's law here. Okay, we can use the fact that F is equal to K, QA, QB over R squared. And we can substitute in what we know. So we know that the force is 2,13 times 10 to the negative 18. We know that K is 9 times 10 to the 9. We know that charge A and charge B are equal to each other. Okay? So that means we can say that this is just going to be the same thing as saying charge A times charge A. So we can say that's the same as QA times QA over the distance between them, which is 2 meters squared. That was in the correct units, we don't have to convert. Okay, and now all we have to do is solve for QA. Okay, it's the only variable in this equation, it's there twice. Okay, so the way we're going to do that is square this, make it a 4, and then multiply that on that side. So we get, okay, I need my calculator, sorry. Okay, so we get 2,13 times 10 to the negative 18 multiplied by 4. So the left-hand side becomes 8,52 times 10 to the negative 18 is equal to 9 times 10 to the 9 times QA, which is QA squared. Now we divide both sides by 9 times 10 to the 9. And we get 9,4666, etc. times 10 to the negative 28 equals QA squared. And to get QA squared to be just QA, we square root both sides. Okay, and we get square root of that is 3,08 times 10 to the negative 14 coulombs. Okay, so the magnitude of the charge on A is 3,08 times 10 to the negative 14. Obviously, we can't tell whether they're both positive or they're both negative, but we can at least find the magnitude on A, and we know that the magnitude of the charge on A is equal to that of the charge on B, so we can therefore say, well, then the charge on B is also equal to 3,08 times 10 to the negative 14 coulombs. Okay, and we're done. And that is all of the examples. Now there is, at the end of the examples for your questions, there's a little reminder of how to convert. Okay, especially with charge, a lot of the time your charge is not going to be given to you in coulombs. It's going to be given to you in milli, micro, nano, or pico coulombs. Okay, so I'm just going to basically write the same thing as it is there. So if you are given millicoulombs, that looks like this, MC, to get from millicoulombs to coulombs, so if you have 1 millicoulomb, that's equal to 1 times 10 to the minus 3 coulombs. So you just tack this times 10 to the minus 3 on the end. Okay, if you're given microcoulombs, that looks like this. Okay, 1 microcoulomb is equal to 1 times 10 to the minus 6 coulombs. If you are given nanocoulombs, okay, then 1 nanocoulomb is 1 times 10 to the minus 9 coulombs. And if you are given picocoulombs, that's PC, 1 picocoulomb is 1 times 10 to the negative 12 coulombs. It's a lot easier to remember than it looks, okay, because you'll see that these exponents in the conversion factors are just negative 3, negative 6, negative 9, negative 12, okay? So you're going down in threes. You're counting in threes and the negatives. So all you really need to remember is the order that these are in. So if you can remember milli, micro, nano, pico, if you can remember that, then all you have to be able to do is count in threes, and you'll easily be able to make the step of, okay, what's my conversion factor? Okay, so just remember milli, micro, nano, pico, and then that will very easily get you to what your conversion factor should be. I actually remember that from when I was in grade 10 or 11, my science teacher just made us learn milli, micro, nano, pico. And that's why I still know that. Okay, anyway, I'm going to stop there. You do have a worksheet to do on this. Please let me know if you get stuck. You've all been quite quiet. Actually, my grade 11 group has probably been one of the less quiet groups, at least you're talking to me, but please do let me know if you're stuck. Okay? I can only help you if I know where your problem is if you're having a problem.